Okay, hi. So in this video we're going to speak about energy transfer in solution. Now in the last video we spoke about measuring the energy released from a fuel when we burn it. But in this video we're going to have a look at the energy released when two chemicals react with each other. Now this is going to be in solution, so it's when you mix two chemicals in solution together and they will react. Now if a chemical reaction causes a release of energy, we call that reaction exothermic. Okay, exothermic. That means that a reaction releases energy into its environment. Now, if you didn't watch the previous video, then I encourage you to do that because we are going to use the same equation and almost the same apparatus to explain the concept. Okay, so again, what we have is a piece of apparatus known as a calorimeter, okay? But this time, whereas in the last video we were using a metal cup, okay, this time we're not. This time we're using a styrofoam cup, okay, or a polystyrene cup. So, styrofoam cup. The reason being is that styrofoam is a very good insulator. And now in this cup, we are going to have the two chemicals which are going to react and release energy. And we want to be able to measure the temperature when that happens, okay? And for us to do that accurately, we need to make sure that as little as possible of that energy is being released into the surroundings by the cup. Whereas if the cup was made out of metal this time, the metal would straight away be releasing that energy into the surroundings, and so our reading wouldn't be very accurate. Okay, and so inside the cup, we're going to have our reaction mixture. Okay, I'm going to call this reaction mixture, and obviously the majority of this is going to be water, because if you have chemicals in solution, normally they're diluted, which means that they contain the majority water. Okay, and here again is a badly drawn thermometer, and that's so we can measure the temperature difference when this reaction actually occurs. Okay, and now just like in the last video, again we're going to use the equation Q is equal to mc delta T. Okay, and just so you remember, Q, okay, is equal to the heat, which is actually, we're going to assume that that is the amount of energy released. Okay, we're going to say that almost all of the energy is released as heat. Okay, M is equal to the mass. Okay, the mass of the water, which in this case is going to be the reaction mixture. Okay, that's the entire reaction mixture. You'll see what I mean in a second. C is equal to the specific heat capacity of water. Okay, we assume that the reaction mixture, bearing in mind it's mostly water because everything is diluted, we assume that the specific heat capacity is the same as it is for pure water. Okay, and that is 4.2 joules, okay, per degree Celsius gram. Okay, and in case you didn't watch the last video, what that means is the specific heat capacity is the amount of energy, okay, joules, required to heat 1 gram of water by 1 degree Celsius, okay? And that's why we've got these units here. And that number turns out to be 4.2. So 4.2 joules of energy to heat 1 gram of water by 1 degree Celsius. Okay, and then lastly, delta T is equal to the change in temperature. Change in temperature. Okay, so now let's take a look at a quick example of an actual reaction. Okay, so I'm going to use the same or a similar example to your book, and rather than give you the actual chemical equations, we're going to simplify it a bit and just use letters, okay? So let's say we have substance A, okay? That's just a substance that we're putting in our reaction mixture, okay? So it's in solution. And we add to that another solution, which is substance B. Okay, now A and B react together in an exothermic reaction, which means we're going to release energy. And we will form our product where these two combine to make C. Okay, so A and B put together will give us our product C. Okay, and what if we had, 70 milliliters of A, and that is containing 0.1 moles of A, in that 70 milliliters. And we also have 50 milliliters of B, which contains 0.1 moles of B. Now, the delta T, or the change in temperature, was 45 degrees Celsius. So if the temperature started at 20 degrees, the final temperature was 65 degrees. So it's risen by 45 degrees Celsius. Now, what we want to do is we want to calculate the energy change, or calculate the amount of energy released. And how we're going to do that is using our formula. Q, which is what we're working out, the energy released, is equal to M times C times delta T. Now, all we do is we sub in for M, C, and delta T. Now, what is our mass? Now, remember, we assume that solutions have the same properties as water. And then in the previous video, we mentioned that a milliliter of water weighs 1 gram. And so how many milliliters have we got in total? We've got 70 of A, but remember, we've also added that to 50 of B. So we've got 120 milliliters. Each milliliter weighs a gram, so we've got 120 grams. Excuse me, so that's M. And now we're going to times that by the specific heat capacity. And we've already said that for water, and we're assuming this acts like water, this is 4.2. Finally, we're going to times that by our change in temperature, which in this case is 45 degrees Celsius. And that's going to give us our answer for Q, which is going to be 22,680, and that's joules. So I'll write it here just a little bit bigger, 22,680 joules, which is the same as 22.68 kilojoules. They are the same thing. Now finally, remember in the last video, we looked at joules per gram and joules per mole. So what about in this example? What if we wanted joules per mole? It makes it a bit more complicated, bearing in mind that we have two different substances. We have A and we have B. And you'll always be working this out with reference to one of them. Luckily, in this case, it doesn't matter which one we're going to use, because both of them are the same amount of moles. That was on purpose to make the question simple. And most of the time, this will be the case in your question. So if we are saying how many joules per mole is this, well, if we have produced 22,680 joules with 0.1 moles, 1 mole is 10 times bigger than this. So we're going to produce 10 times the amount of energy. So what we'd do is we'd do 22,680 joules, times by 10, because that would give us 1 mole, is equal to 226,800 joules, which is the same as 226.8 kilojoules per mole. Just about fit that there. 226.8, let's do that down here. 226.8 kilojoules per mole. If I'd have started with 0.2 moles, I would have only had to times it by 5. If I'd have started with 0.5 moles, I'd have only had to times it by 2. We just want to get to 1 mole, so we can say per mole. The other way that you could work that out, which is going to work every time, is if I'd have done 22,680, if we're doing it in joules, 680, divide it by how many moles you've got. Divide it by 0.1, that's the same thing as times it by 10. If I had something like 0.3, you just divide it by 0.3, and then that's going to get you your answer as well. And so I'm going to stop there. That's basically the kinds of calculations that you're going to see. All you need to do is realize that a solution acts like water. Okay, so we assume that it has the same specific heat capacity as water, and we assume that the mass of 1 milliliter or 1 centimeter cubed, they're the same thing, is 1 gram, and then we can just plug it into the equation that we used previously, and we can work out the amount of energy released. Okay, so lastly, just remember that when we are doing these questions, there we go, we are using a styrofoam cup if we're going to carry this out in a lab, just so that we can stop the heat energy from escaping. Okay, if we were using a metal cup, it would escape quicker. All right, so I'm going to stop there. I hope that helped clear things up if it didn't make sense. As usual, please, if you do have any questions, feel free to post a comment below and I'll get back to you, or send me a direct email using the link in the description. But please remember to subscribe and to like the video, because there will be more coming, and I look forward to seeing you in the next one.